This next section we're going to get into is the sum and difference formulas. And what these formulas are going to help us with are when we add or subtract angles of sine, cosine, and tangent. Now, as we talked about in the previous chapter, we said that the sine of a plus b does not equal the sine of a plus the sine of b. We said it was impossible to distribute the sine in. And really all I said was trust me on this. We cannot distribute the sine in. But we want to show in this section how do we deal with this situation and what does sine of a plus b truly equal if we can't distribute in the signs. So just as a little confirmation for you guys why this fails, let's do a little suppose. Suppose angle A is equal to 21 degrees and angle B is equal to 35 degrees. I'm going to do a little bit of substitution here. The sine of 21 plus 35 is equal to the sine of 21 plus the sine of 35. Now I'm going to show that this is false, so that's why I've got that equal sign right here. In the end, we're going to see it doesn't work, but let's say this is true, and we're going to show why it doesn't work. So if I simplify inside my parentheses, 21 plus 35 is going to be the sine of 56 is equal to the sine of 21 plus the sine of 35. Now if I plug sine of 56 degrees, sine of 21, sine of 35 degrees into my calculator, I'll see the sine of 56 is 0.829. The sine of 21 is 0.338. Actually, it's 0.358. Can't read my calculator. 358. And then the sine of 35 is going to be 0.574. And if I add the right-hand side, they're 0.358 and 0.574, that equals 0.932. And obviously 0.829 is not equal to 0.932. So algebraically we can see that doesn't work. But for those of you who are geometric learners, let's look at this from two triangles. I've got triangle A and triangle B right here. Angle A, angle B. And I want to find the sine of A plus B. Well, I know sine of A is the opposite side here, and I can say that because I've got a unit of 1. So these would fall in the unit circle. So sine of A and sine of B, if I'm truly adding sine of A plus sine of B, that's the picture that I'm getting. Sine of A plus the sine of B, combine them together, get some large number. But you can see right there, my angles aren't being added. These are two separate triangles. The sine of A plus B that you see right up here is truly this setup, where you're adding the angle measurements together and making a larger triangle. And you can see now that my opposite side does not go way up here, which was that sine of A plus B. Rather, the sine of B is sort of on a diagonal, and my new triangle that I create is actually going to be where I put this pen down. I would drop a vertical there, and that's my opposite side of the new triangle. So the sine of A plus B is not adding the opposite sides like we see there. So the question then is, what is the sine of A plus B? What does it equal? And that's what I want to prove to you today using geometry. I'm going to take those two triangles that I just had on the piece of paper, those yellow triangles, and I'm going to draw them out visually here. So I'll start here. And that's a horribly drawn rendition of it, but it'll work for what we want to accomplish. Down here is going to be angle A. In there is going to be angle B. And right here would be triangle A. And right there would be triangle B. So here's the first triangle, here's the second triangle. That's sort of trying to simulate what I had right here where I put the two triangles on top of each other. I just drew these lines a little long, so if you were to cut those off, that's really what I'm trying to simulate here, the two triangles on top of each other. This whole big thing here is then A plus B, putting the two triangles together. And I need to drop a perpendicular down so that I can find the opposite side. Now, there's one other piece that I'm going to fill in, and it's this little triangle that you see up there, this very little triangle. And it's going to help us simplify down our problem. So now what I'm going to do is I'm going to label all the important points that I've got on here. Point A is going to be an important point. Point B up here where the perpendicular comes down. Point C where that line intersects the triangle. We've got point E and F, which is the outside of this triangle, the triangle A. And then the other point that's important is this point D, sort of on the inside right there, that smaller triangle that we're going to be working with. And all these angles right here are going to be perpendicular. 90-degree angles right there. So what I want to do now is I want to figure out what does sine of A plus B equal in terms of A, B's, D's, E's, and F's. And the way I'm going to do this is I'm going to work with all four triangles. The four triangles, just in case you don't see them, triangle A, which is AEF. We've got triangle B, which is BAE, and those are the two triangles that I originally started with. We then get triangle BCA, which is angle A plus B, that bigger triangle. And the last one is triangle BDE. So really what we've got here is we've got triangle AEF, which is my original angle A that I was working with. We've got triangle ABE, which was my angle B. I've got triangle ABC, which is angle A plus B. And then I've got this last triangle that is BDE, that is sort of this unknown triangle that's just sort of in the middle of the problem. So let's start by looking at sine of A plus B. Sine of A plus B, the angle A plus B, is triangle ABC. So I'm looking at triangle ABC here. And the sine we know is opposite over hypotenuse. So starting off, the sine of A plus B is going to be the opposite over the hypotenuse. And in this picture, it's going to be BC, which is the opposite, and the hypotenuse is AB. So I'm just going to represent the sine in terms of line segments. The next piece I want to look at then is what can BC be rewritten as? Because ultimately, this BC over AB, that's really a reduced version of what the line segments truly are. So we're going to unreduce it and expand it out to figure out what does this picture really represent. So if I look at my picture, can I write BC as two other line segments? And the answer is yes. I really have two different line segments I can work with. I've got BD and DC. Those add up to be BC. Or I could go BD plus EF equals BC. So I can rewrite BC in two separate formats. And I'm going to rewrite BC over AB as BD plus EF all over my hypotenuse still. So BD over EF is equal to BC. And the reason I did that is as soon as I broke it up, I'm now dealing with two separate triangles. This EF piece is part of angle A, And this BD piece is that unknown triangle that we're trying to work with. If I did DC, I would have a triangle here, but it's not really defined at that point, and I sort of just have this ambiguous line I really don't know what to do with. So now that I've broken down BC, this segment, into BD and EF, I'm going to rewrite this as two separate fractions. So BD over AB plus EF over AB. Now, as I said, this is a fully reduced version of an equation already. What did I cancel out? And this is where you got to think back algebraically. If I had the expression 9/2, that can be written as 9 over some number times some number over 2. So this could have been 9/4 over 4/2. And then the 4's cancel out, and then you're left with 9 over 2. Or this could have been 9 over 7 times 7 over 2. And the 7's cancel out, and you're left with 9/2. So with each of these segments here, something has been canceled down. So I'm going to rewrite this line segment as BD and AB as two separate fractions with some unknown that was canceled out. And then the other part here, EF and AB. And something was canceled down. And we need to figure out what that something was. And what we're going to do is we are going to look at the triangles that make up each of these pieces. So right now, if I look at segment BD and segment AB, so here's segment BD and here's segment AB, which side of a triangle is common between both of them? So if you look at side BD, it's a part of triangle BDE. You look at side AB, that's a part of BAE. What side is common between both of those triangles? And if you look at it, side BE is the common side. So here, ABE, this BE, and for BDE, BE is in there. So BE is the common piece that ends up being canceled out. So if I were to take this expression and simplify it, it's the exact same thing as BD over AB. We'll use the same thought process down here. EF over something times something over AB. So I see segment EF, which is right here, and I see AB, which is right there. So what side is common between both triangles? So I've got triangle AEF and ABE. And the answer for the common side is AE is common between AB and E and AE and F. So AE is the piece that was canceled out. So now you look at that and you say, great, I've got four fractions right there. We know what they are, but what is that in terms of sine, cosine, and tangent? And that's the final thing we want to look at. Couple things that we need to know. The first thing is that this right here is angle A, and this is going to be a little hard to see, but this line right here that's DE continues forever. And so it's parallel to the line AF, which means inside here, that's also angle A. So this part inside of here is angle A as well, because alternate interior angles are congruent. Let me blow that up a little bit because that's going to get really tight. So we'll draw this. Just redraw this a little bit. We know that right here is angle A, so this piece in here is going to be angle A as well. Which then means this angle over here has to be 90 minus A, and the angle at the top there is going to be A. So there's three places that we see angle A where they're all equal. It's down here, it's the alternate interior angle, and then it's the angle up here. So in terms of this diagram, angle DBE is congruent to angle A. And that's going to help us as we go along here. So now that I know that piece of information, I can figure out what all these are. BD over BE. So BD over BE. Since I know this right here is angle A, this is the adjacent side and the hypotenuse. So BD over BE is the same thing as the cosine of A, adjacent over hypotenuse. BE over AB. So BE over AB, I'm looking at the angle here, which is B, the opposite over the adjacent, which is going to be the sine of B. EF over AE. So EF over AE are the two pieces I'm looking at. So I'm dealing with angle A here. Opposite over adjacent is going to be the sine of A. And then AE over AB, which is up here, that is going to be the adjacent over the hypotenuse of the cosine of B. So the sine of A plus B is this long expression. Cosine of A, sine of B, plus sine of A, cosine of B. So it's not as easy as just distributing in. You've got this extra cosine A, cosine B piece that you need to be aware of.